In this lesson, we're going to look at what's called normal distribution. We're going to determine the properties of a normal distribution and compare normally distributed data. Sometimes the distribution of data has a special shape. For example, the purple graph has one peak, so the shape has one mode. We want to describe the shape of each graph and suggest a context that the graph could represent. So if we look at the purple graph, this is what we call mound shape. It has one peak that is roughly symmetrical about the middle. So roughly about the middle, it looks the same on each side. An example where this might occur is the amount of time spent practicing a musical instrument. Okay, maybe there's a certain time of day where most people do their practice. Fewer in the morning, fewer late at night. So that's just one example. The red graph is what we call a skewed graph. Skewed is when it's off to one side, whether it's the left or the right. In this case, it's all off to the right. There's still one peak. An example for this might be marks on a test. Not a lot of people have the low-end marks, and a lot of people are maybe in the 70s, 80s, and less are in the 90s, 100s. Bimodal is what we would call this blue graph. There are two peaks that are roughly symmetrical about their middles. For example, here, maybe this represents the number of texts sent during the course of a day. So maybe there are some time frames in a day where most people send their text messages. And then there's other times when not a lot of people send. And the last one is what we call uniform. There's no peaks, and it's flat. For example, the number of minutes it takes you to walk to school over a 2-week period is going to be roughly the same amount each day. So histograms can come in these different forms. And we're going to look at one particular type. Many games require dice. For example, the Yahtzee requires 5 dice. What we're going to look at right now is what shape is the data distribution for the sum of numbers rolled with dice using 2 dice. So if we were to roll 2 dice and record their sum, and we were to repeat that process over and over again, is there a sum that's going to occur more often than others? Is there a certain sum that's rarely going to occur? And we can actually simulate this here. So what we have is we're going to find the sum of 2 die, and we're going to do 999 rolls. And we're going to see if there's a certain sum that occurs most often. So you can watch the combinations, and as you can see, it's recording each sum, and it's adding it to the graph. And as you can see right now, sums of 6 and 7 seem to be occurring more often. 7 is in the lead, whereas sums of 2 and 12 are not occurring very often. So this is going to continue for 999 different rolls. And we're going to see what kind of a graph we end up with. Seven still is occurring the most. And what you should be noticing is that roughly each side is symmetrical to that middle. We're almost at 999 rolls. So as you can see, this graph ended up being roughly symmetrical about the middle. We definitely had a distinct group. The 7 occurred the most often. I'm going to actually increase the speed so that this happens really fast. And we're going to run it again and see if we get similar results. So we're going to put new and we're going to run it really fast. As you can see, 7 didn't occur as often, but it's still roughly symmetrical. Let's try it again. Again, roughly symmetrical. You could repeat this process over and over again, and each time it is going to end up being roughly symmetrical about the middle. This was like the purple graph on the first slide, where there was just one peak, one mound. There's a special name for this, and it's called normal distribution. And it's data that, when graphed as a histogram or a frequency polygon, results in a unimodal symmetric distribution about the mean. The curve is referred to as a normal curve or bell curve. Some of you may have heard of the bell curve, and your parents maybe went to university and talked about being graded on the bell curve. In the past, universities would often mark like this. A certain percentage would fail, a certain percentage would get A's, and the majority of them would get maybe C's or something like that. And they would have certain percentages of people fit into each of those categories. What you will also notice about normal distribution is that it has certain properties. 68% of the data are within one standard deviation of the mean. So I want to point out a number of things here. This is our mean, our average. So that's where we always start our normal distribution. We start with the mean. We would have to find standard deviation, and in the previous lesson we learned how to determine what standard deviation is. So what we would do is we add to the mean what that standard deviation is, and we fill in this spot. We add the standard deviation twice to the mean to fill in that number. We add the standard deviation 3 times to the mean to get the third spot. Then we reverse the process and we subtract the standard deviation from the mean once. Here we would subtract it twice, and here we would subtract it 3 times. And in a normal distribution, you will always get these same properties. So 68% of the data, 34 plus 34, is within one standard deviation of the mean. 95% of the data are within 2 standard deviations. So if we were to add up this, and this, it would add up to 95%. 99.7% of your data are within 3 standard deviations. You will always have outliers, which is why we have the 0.15 on each end. They are the ones that will lie outside of 3 standard deviations. So how can we use this? Well, we can answer questions like this. The speeds of 1,000 cars were recorded by photo radar. If the data collected was normally distributed, so that's important, it's got to be normally distributed, with a mean of 105 kilometers per hour and a standard deviation of 10, determine what percentage of cars traveled between 105 and 115 kilometers per hour. So what we can do is we start by sketching ourselves a normal distribution. And what we know is that we will always have our mean, and we will always have 3 values to the right and 3 values to the left. So we can always start by drawing a normal distribution this way. This question tells us that our mean is 105. So we can place 105 in the mean spot. Standard deviation of 10. So what we do is we go 105 plus 10, and we get 115. Add another 10, 125. Add a third, 135. Repeat the process. Subtract 10 to fill in our left-hand values. So 95, 85, 75. Now we are looking for the percentage of data that is between 105 and 115. So that's in this range right here, between 105 and 115. Now, if we go back to our percentages, that is the value between the mean and 1 standard deviation. 34% of your data falls in that range. So 34% of the cars recorded were traveling between 105 and 115 kilometers per hour. So again, same question, but this time we want the percentage of cars traveling less than 95 kilometers. So if we set up our normal distribution again, and we'll just practice it to get really good at it. Our mean is 105. We know we have 3 to the left. We know we have 3 to the right. We're adding our standard deviation, and we're subtracting our standard deviation. Now what we want in this case, we want less than 95. So that is this data in here. So if we go back to our chart here, 95, here's our mean. 95 was at -1 standard deviation. So we want the data that's all to the left of -1. So we need to add 0.15% plus 2.35% plus 13.5%. And when we add those together, we'll find the percentage of cars that were traveling less than 95 kilometers an hour, 16% of the vehicles. Same question, but we're going to change it. Now we're not looking for the percentage of cars, we are looking for the specific number of cars that are traveling between 85 and 105. So again, let's set this up. 105 is our median, so we have 115, or is our mean, sorry, 125, 135. Then we've got 95, 85, and 75. And we want the data of the number of vehicles between 85 and 105. Remember, 105 is our mean. So we are looking for the percentages that are 2 standard deviations below. So we start, we've got 13.5% plus 34%. So the percentage of vehicles that are in that range are 47.5%. Now we knew that there were 1,000 cars recorded. So what we want to do is we want to find 47.5% of 1,000. So all we do is we go 1,000 times, now we turn our percentage into a decimal, so you divide it by 100. So 0.475, and we have 475 cars that traveled between 85 and 105 kilometers per hour. Same question, this time we want the number of cars between 115 and 125. So you've got your normal distribution, 105 is your mean, add your standard deviations 3 times, subtract your standard deviations 3 times. We want the values between 115 and 125. So here was our mean. So we are looking for the percentage of data that is between the first and second standard deviation. So we are looking for 13.5% of our data. That's what falls here, because we've got a 34 and then our 13.5. So you got 13.5% of the vehicles. So you go 1,000 times 0.135, divide your percentage by 100, and you have 135 cars that traveled between those speeds. So in summary, graphing a set of grouped data can help you determine whether the shape of the frequency polygon can be approximated by a normal curve. So we use a histogram or a frequency polygon, and you'll be able to see if you get a normal curve out of it. You can make reasonable estimates about data that approximate a normal distribution, because data that is normally distributed has special characteristics. So we know certain percentages of the data fall within certain standard deviations. So it's really easy to make estimations as to how many things occur in a certain range of data. Normal curves can vary in 2 main ways. The mean determines the location of the center of the curve on the horizontal axis, and the standard deviation determines the width and the height of the curve. All right, we're not going to look too much about the height. We're dealing more with the width and the percentages. So the property of the normal distribution can be summarized as follows. The graph is symmetrical. All right, so the mean, the median, and mode are equal or close and fall at the line of symmetry. So we deal with the mean. The normal curve is shaped like a bell, peaking in the middle, sloping down towards the sides, and approaching zero at the extremes. About 68% of the data is within 1 standard deviation, 95 within 2, and 99.7 within 3. The area under the curve can be considered as 1 unit, since it represents 100% of the data. Generally, measurements of living things, such as mass, height, and length, have a normal distribution.